Okay, let's talk a little bit about the regression model. This is the equation of our best fit line that fits to our data, and so the formula for that regression line is, we'll express it in intercept slope formula. Beta 0 is the y-intercept, beta 1 is the slope, and we'll write the line, we'll express the regression line as y is equal to beta 0 plus beta 1 times x. So our data model is that we can represent any of our y values as beta 0 as a deviation from our regression line, and we'll let that deviation be epsilon. So in our scatter plot, where this is x and this is y, and we've got some points here, and we get our regression line, and we'll see how to calculate this, the parameters of this line in a future lecture. But here, if we call this x1 and this y1, similarly this point would be x2 and y2, then the vertical distance between y1 and the line is our epsilon 1 value. So it represents kind of an error term or a deviation between the actual data value and the distance to the line. So our assumption now is that these epsilon values, these deviations, are normally distributed with a mean of 0, and then standard deviation that we'll represent as sigma. So these have a normal distribution. Okay. For any value of x, y will also be normally distributed, and we can compute the expected value of y. It's the expected value of this. The expected value of epsilon is 0, so the expected value of y, which in your book I think you denotes as mu of y for a particular x, so dash x, is equal to beta 0 plus beta 1 times that x. So the expected value of y actually depends on the particular x value that we're evaluating the expected value of y at. The variance of y is, alternate notation, is just sigma squared. It's the same as the variance of epsilon. So y is normally distributed with expected value equal to b0 plus b1 beta 1x, and variance sigma squared. So let's look at an example. This is exercise 12.8 on page 476. And here, if I recall, the data is dealing with strength of concrete, and y is what's known as the standard strength, or the strength measured after, I think, 28 days. And then our x data is something they call the accelerated strength. I think it's the strength after a much smaller interval, and they're trying to use the x data to make statements or inferences about the y data. Now, the regression line is given as y is equal to 1800, so that's the intercept, plus 1.3 times x. And we'll see in the next video how to actually compute the models of this regression line. But in this problem, the regression line is given, and the standard deviation of the deviations is 350. And in part A here, they ask us to compute the probability that y is greater than 5,000, given that x, the accelerated strength, is equal to 2,000. Okay, so we compute the expected value of y at this value of x. So the expected value of y is 1,800 plus 1.3 times, I plug in this value of x, and I get 4,400. And the variance of y is actually just the variance of epsilon, or 350 squared. Okay. But since y is normally distributed, I can compute this probability using the same steps that we've used in the past. I standardize the random variable, so this will be the probability of z, the probability that z is greater than, I standardize by subtracting the mean and dividing by the standard deviation, which are, well, I'll write it out. Again, at this value of x, I'm going to subtract 4,400 and divide by, not the variance, but the standard deviation, so 350. So this is the probability that z is greater than 1.714, and so where z is my standard normal random variable. Of course, I can get this probability from the CDF, which is our phi function. Of course, my CDF gives me the probability that z is less than 1.714, so I subtract that from 1 and I get the desired probability. So either looking this up in a table or using the norm CDF function in Octave that evaluates to 0.957, the CDF of the standard normal random variable at 1.714, and the final answer is 0.043. So I can use my regression line to make statements about probabilities here. So in the next video, we'll look at how do we calculate the slope and intercept for a given data set.